So, finishing up, we're kind of up to the stuff that we've been doing really recently. So a recursive function, you've got two pieces to it, right? So
you keep on shifting, so it'll work.
No microcontroller, no plan.
All right.
All right, so there's a classic recursive function. So if n is less than or equal to 1, the function's equal to 1. Otherwise, it's equal to f of n minus 1 plus f of n minus 2. It's the Fibonacci function. But any recursive function, you can basically write your function in terms of smaller values of it. If you've been playing along in 222, this is the max val function. This is the rod cutting problem. This is all this stuff. This is the height function. So we talk about it in here a little bit. Pigeonhole principle, so if you have n objects and you have fewer than n bins to put them in, at least one bin is going to have at least 2 objects in it. That's the hand-waving definition of the pigeonhole principle. There's a formal definition, but basically if you got more things than you have places to put them, you're going to have to at least double up somewhere. So you should know that. Counting, so product rule, sum rule, and principle of inclusion, exclusion. So product rule is when you can break a task into a succession of tasks. You're going to do this, and this, and this. The number of ways to do the first task is the product of the number of ways to do each of those subtasks. The sum rule is when you can do a task by doing task 1 or task 2 or task 3. And the number of ways to do your original task is the sum of the number of ways to do each of those possibilities. Right, and so the and is multiplication, the or is addition, just like 250, just like set theory. Okay, it's always coming up. Inclusion, exclusion is the bit where you have students who like the first Star Wars movie and people who like the second Star Wars movie, and some people like both of them. And you want to know how many people have an opinion, and it's this thing. So the number of things in the union is the number of things in each set minus the number of things that are overlapping. So A might be the set of people who like the first Star Wars movie, and B is a set who like the second Star Wars movie. And if you add those together, you don't get the total number of people. You get the total number of people plus the number that like both movies. So if you subtract that out, you'll get the number of people. And so you can use that in various forms. Permutations are ordered, combinations are unordered. So that's quiz 3. Pascal's triangle, I'm not going to ask you about, but you know, it's that thing. And this is always combinations. And binomial theorem, I'm not going to ask you about either, but these are the coefficients of a plus b to the n. Go down to the nth row, and those are the coefficients of the different monomials. And we waved our hands through an explanation of why that is, and it has to do with FOILing multiple things and choosing which things you're going to pick a first term from, which you'll pick the second term from, and it comes back to combinations. What should you know about graphs? There will be graphs on here. So graphs are composed of vertices and edges, right? You always have at least one vertex. You don't necessarily need to have any edges. Directed, there's a direction associated with an edge. Undirected, there's not. Degree of a vertex, so just the number of edges at each vertex gives you the degree. Adjacency matrix, so it's a way to represent graphs, say, in a computer. So here's A, and here's B, and here's C, and here's D. So we could make a matrix like this. And anywhere there's an edge, we're going to put a 1, so A is connected to B. And anywhere there's not an edge, we'll put a 0. And B is connected to A and C and D. And C is connected to B and D. And so there's an adjacency matrix. The other thing you can do is an incidence matrix. With an incidence matrix, you list vertices on one side and edges on the other. And then you indicate which vertices are incident to which edges. So A is incident with E1 only. And B is incident with E1, E2, and E3. C is incident with E3 and E4, and D is incident with E2 and E4. There's different ways of storing these things, say in a computer. Mostly adjacency matrix is the one we typically go to. Isomorphism of graphs means that there's a one-to-one mapping from vertices to vertices that preserves adjacency. In hand-wavy terms, it means you can morph one graph into the other without having to break things. So you can stretch edges and move them around and twist them and so on, and turn it into the other graph. That's basically what a one-to-one function would do to the vertices. Euler Path. So what's an Euler Path? Oh, I already put it up here. So you travel each edge exactly once. An Euler circuit starts and ends at the same vertex. So your goal is to go through each edge exactly one time. A Hamilton path goes through each vertex exactly once. So this graph, there's an Euler path. I could start here, go over, come down to C, go up here, and come back. And I've hit all the edges. And there's a criteria for the existence of an Euler path. Do you remember what that is?
It has to have an odd number of at least 2 vertices have to have an odd number of edges.
So actually at most 2. So if there's an Euler path, exactly 2 vertices will have an odd degree. If there's an Euler circuit, then no vertices will have an odd degree. They'll all have even. So count the number of things in and out of each vertex. That's got a degree of 2 and 2. That's got a degree of 3 and 1. So there's only 2 with odd degree that has an Euler path, but no Euler circuit. Hamiltons, we don't have a criteria like that for. And then Dijkstra's shortest path algorithm, so there will be a question on Dijkstra's algorithm. So if you like Dijkstra, there's a free problem. And grammars and languages. So this was all the stuff that we talked about, but the only thing I'm going to ask you on the exam is related to phrase structure grammars. So remember, most of this is about production rules. So we have a start symbol. We have a set of terminal symbols, let's say 0 and 1. We have a vocabulary, which is say 0, 1, R, A, and B. And then we have production rules, and our production rule might be R can go to lambda, R can go to 0, 1, R can go to A followed by B, A can go to 1 followed by B, and B goes to 0. That's a really goofy language, but that's okay. So that's a phrase structure grammar. We can say what are some things that are recognized by this. So someone should be able to tell me really quickly at least one string recognized by this.
Nothing.
Yeah. So our start symbol R can go to the empty string lambda, so that's definitely part of the language. What's another one? 0, 1, because our start symbol can go to 0, 1. Yeah, so R can also go to AB, and the only thing A can go to is 1B, and the only thing B goes to is 0. So 1, 0, 0. And is that the only thing in our language?
Well, you could just have 1, 0, right?
How would you get that?
Oh, no.
Yeah, so if B could go to lambda, you'd also have 1, 0.
Yeah.
So I told you it was a weird language. So I think that's the only thing in the language. But that's just an example. So the other, so that's analysis, and that's usually straightforward. You can build little trees or something like that. And start from your start symbol and just see where you can get down to whatever your terminals are. The trickier version is synthesis. So let's say we want a language that consists of any number of zeros followed by a 1. And let's say our start symbol is R. So how do we find production rules that produce this language? Well, I don't know. It's trial and error. But the more you analyze these, the better you are at coming up with things to try. So if you want to get better with this, go through the exercises. And the chapters in the book that talk about grammars are way more complex than what we've been doing. But it's just a practice thing. So ideas, how can we produce this language with some production
R can
rules?
go to AB.
Okay, so let's try R goes to AB.
A can go to, yeah, A can go to the empty set, or A can go to 0, A.
Okay. So what does this get us right here?
1 and any amount of zeros.
That just gives us infinite zeros.
That just gives us any number of zeros, right? So it could be no zeros, or it could be a 0 followed by nothing, or it could be a 0 followed by a 0 followed by nothing. So this right here gets us the beginning part, any number of zeros that we want, including none. Okay, so what about B?
Could we just do,
B can go to 1.
can we just do R goes to A1?
Yeah. So we could have R goes to A1, and then A can go to lambda, or A can go to 0, followed by A. Same thing as that. So play with those, post questions if you got them, but like I say, it's really just kind of a practice thing. Like all things synthesis, like synthesizing state machines or programs. And I'm not going to ask you about state machines, state diagrams, or Turing machines. Or I won't ask you to prove P equals NP. But if you do, I'll give you 10 bonus points, which you can pull with your $1 million prize. Have you ever looked at the Millennium Prizes?
Top 1P versus NP.
Yeah.
People do these and then don't accept the $1 million.
Why?
I don't know. Like they say it's for pure mathematics and stuff. Okay, you can do it for pure mathematics, but they're handing you $1 million.
Yeah,
Just
a
take
million's math, you know.
only
It's a
one
number.
guy.
It's what?
It was one guy
Yeah.
who solved one, and he didn't want the prize, but mostly he didn't want his name attached to it.
Oh.
The only reason people even knew that he did it was because some other dude, like he had submitted it anonymously, and some guy in China was like, "Hey, that was me."
Really?
And then he came out of the woodworking and was like, "All right, I don't want the prize, but
Right.
I do
Don't want
not
someone else
want
either."
someone else to get it.
Yeah.
For doing it, because that defeats the whole purpose of
Yeah.
putting my name.
Well, Sartre declined the Nobel Prize in literature because he didn't want to be tainted by it.
Well, didn't like Bob Dylan get like the prize and he just didn't show up or something?
I think he didn't show up, but I think there was a reason.
Because he just doesn't show up
But
and stuff. He's
maybe.
Bob Dylan.
But yeah, just the fact that he got that was amazing. I was like so happy. Made me feel good about life. So yeah, these prizes are $1 million each. So P versus
Is it
NP.
taxed, though? Is it taxed though?
I don't know, because Nobel Prizes aren't because you don't seek them, but I think if you submit to this, it might. I don't know, actually. It's a wiggle room.
P versus NP is actually a munition of war, and you're getting paid by a foreign body for solving it. So now you're.
That's right. Yeah, and you have to spend your money on cigarettes. So yeah, these are interesting questions. Riemann hypothesis is nuts. Prime numbers.
It's not like a joke solution to it. That was just like think of the biggest prime number you can, and then think of the one bigger than that. You've solved the Riemann hypothesis.
Hey, there you go. It sounds like something from The Simpsons.
So what exactly, is it just asking for what's the biggest prime number, or if it's...
No, it has to do with something called the Zeta Function,
Oh,
which is related to distribution of primes, and it gets into really crazy stuff. And I have a really good book on the Zeta Function that actually was simple enough I was able to understand it, because it had always boggled me. Yeah, it's only been around for like 150 years.
And you
So
only need to
non-obvious
find
zeros with
one-
Zeta Function have real parts of 1/2.
You only need to find one number. It's kind of one of those either prove it right or prove it wrong.
No, so this is actually, you can relate it to primes, but it's actually asking for a proof of a statement. So it's more complex than just finding one thing. I think all of these are like that. All right.
Isn't there one where it's take any number and then if it's odd, divide by 2?
Yeah, that's an open question. I'm trying to remember what that's called. It's iterative function and
Either prove it always goes to 4,
Cool.
2, 1, or
yeah,
disprove
it always ends at some number, but no one's proven it. Yeah, I can't remember the name of that, but it'll hit me later. All right, so that's
feel
pretty
like
much it.
that one wouldn't be that hard to prove though.
Yeah, I mean it's a simple function from what I remember.
Yeah. And all you have to do is just use the definitions of odds or evens and
Yeah.
kind of fit in there.
Yeah, go for it. A lot of these things, if they're eventually proven, it's not going to be by the people who have been doing the same thing for 100 years. It's going to be by someone who comes at it with a totally new perspective and just says, hey, all you got to do is this. So, all right. So, enjoy the weekend, and I will see you on Monday at 12 for your exam. Thank you for the class.
I'll see you.